So this first, so we have three talks in this session. So first talk is by Saroj Kumar Nandi from TIFI Hyderabad. So he's going to talk about non-trivial effects of activity on glassy dynamics in active systems. Yeah, please.
I'll be talking about some non-trivial effects of activity on the glassy dynamics in particulate active systems. If you take a liquid and quench its temperature below the melting point, then it can go to the crystalline phase, which is the thermodynamically stable phase. However, crystallization is a time-consuming process. It requires two processes, the nucleation and the growth of the crystalline phase. Instead, if you somehow avoid this crystallization, for example, cooling fast or some by other means, then the system doesn't go to the crystalline phase. Instead, its relaxation time and viscosity keeps increasing, and eventually it becomes difficult to keep it equilibrated. So this is the state that we call glass. One working definition of the glass is when the temperature becomes such that the relaxation time becomes of the order of 100 to 1000 seconds. If you take a snapshot of a glass and that of a liquid, it's very hard to distinguish between them. They are nearly the same. However, their dynamics are quite different. For example, this 2-point autocorrelation function, density autocorrelation function, for the liquid phase, it decays exponentially fast. However, as we approach this glass transition temperature, the glass state, then the relaxation becomes complex. It first decays towards a plateau, and then from the plateau at very long time towards the zero. Also, this is known as the Angel plot representation, where viscosity as a function of Tg over T, viscosity or relaxation time both works in this way. In this semi-log plot, some of the curves they fall near this Arrhenius line, the state line. Those are known as strong glasses, and some others deviate from this Arrhenius line, and those are known as fragile glasses. And for some others, it can also happen that they fall in the other side, known as this half-Arrhenius relaxation scenario for those systems. Another typical characteristic of glassy system is known as the dynamical heterogeneity, where fast-moving and slow-moving regions coexist at the same system at the same time. This is also a typical characteristic of the glassy system. Now, why this problem is interesting and important? Because we see glassy behavior everywhere in our real life in different scientific problems. For example, in real life, window glasses, glass utensils, artwork, etc. In different scientific problem of condensed soft matter system, hard condensed matter system, computer science, optimization, etc. Also recently, it has been shown that several biological systems for whom glassy dynamics are quite important, and I will give some of the examples of those systems. So three different types of example. The first type of example is cellular cytoplasm. So this is the fluid inside the cell. And in the year 2001, the group of Jeff Fedberg, they showed for the first time that the cell cytoplasm behaves as a glassy material existing close to the glass transition. And several important works followed where they showed typical glassy characteristic, for example, this subdiffusive mean square displacement, deviation from this Gaussian behavior of the Van Hove correlation function, a typical characteristic. And also this is this Angel plot, viscosity as a function of phi over phi g, where this is for the cytoplasm of a osmotically compressed cell. And it turns out that the property of the system changes with metabolic activity. And this is for a reconstitution in vitro. So they took some myosin molecules and actin filament and mixed them outside of the cell, and then they measured the behavior of that system. And as activity increases, the curve moves towards the strong glass behavior. Also, this is another example where they showed this bacterial cytoplasm shows glass-like properties, and the metabolic activity of the system fluidizes the glassy behavior of the system. This is the second type of example, and this is known as the biomolecular condensate. So cells are active objects, and they must organize their biochemical reactions. The way that they do it is via compartmentalization. And there are mainly two types of compartment inside the cells. Some of them have membrane and some of them don't. Now, when the membrane, the compartment which have membrane, how they exist inside the cell is easy to understand. However, how the membrane-less compartments, they form and coexist inside the chemically active environment inside the cell remained a puzzle. And one of the mechanisms was proposed in the 2009 that these membraneless organelles, or this biomolecular condensate they used to call, they form via phase separation. Very recently, it has been shown that these biomolecular condensate, they show glass-like property. For example, the viscosity strongly increases with their age. No significant change in the structure at the same time. So this is glassy characteristic. These are some data shown for the P granules that appeared in this paper. And in this paper, they modulated the strength of the phase separation, and they show that the viscosity again depends on the strength of the phase separation in that system. And this is the third type of example where collective motion of cells. So this is typically on a monolayer of cells. This is known as epithelial monolayer. And this type of dynamics, the glassy dynamics, are crucial for several biological processes such as wound healing, cancer progression, development, etc., where they again showed some glassy characteristic. For example, this cell dynamics and the shape changes during this wound healing. This is a comparison between the healthy monolayer and the cancerous monolayer. But these systems are quite complicated and understanding, so they have many defined characteristics and they have control parameters which are quite different from the particulate system. So one of the form that how they are different from the passive system is activity. So they do consume some energy and do some work, and this work can be quite different. For example, this system, the constituent divide, die, differentiate, decide their own fate, propel themselves, change conformation, modulate interaction, can be confluent, etc., etc. So clearly, developing a theoretical framework for these systems are quite difficult, and the idea is to take one aspect of this activity at a time and try to understand it in detail, and then think about all of the other properties within those systems. So let me give one concrete example that we are also interested in our group to understand where activity is quite crucial for the glassy dynamics, and this is known as the epithelial to mesenchymal transition, EMT. So epithelial monolayer is the healthy monolayer where you have a cell monolayer which is confluent, that is cells entirely occupy the space, there is no cell-cell gap in that monolayer. And in that case, so we are looking from, for example, this is the monolayer, let's say, and we are looking perpendicular to this. And those cells have out of plane polarity. So these cells have this type of polarity where we are looking from the top. So this is a movie from our experiments that we are doing in TIFR Hyderabad. One of the characteristics is the cells have out of plane polarity. They have strong cell-cell junction. So there are different proteins that make the cell-cell junctions quite strong. And the dynamics in this system is quite slow. So this is glass-like sedentary. They do not move much. In contrast, when they become mesenchymal, then this out of plane polarity is lost. Instead, the cells become in plane polarity, and then they become motile. So they become active. And in that case, the cell-cell junctions become relatively weak, and in that case, activity basically fluidizes the monolayer. And ironically, the same process, this transition from epithelial to mesenchymal transition, are crucial both for development in the healthy scenario, also for cancer progression. So it is quite important to understand how activity affects the glassy dynamics in this type of system. So here we will focus on this particular aspect of activity and a much simpler system, which is the point particle system. These systems, they are associated with these particles are associated with a director. The particles move along this director with a particular force F0, which is self-propulsion force, for a particular time, tau p, which is the persistence time. So this represents a much simpler system to understand, and also they already have quite interesting properties. So it is intriguing to study these systems. I'm going to discuss two particular aspects in this system. One is known as the dynamical heterogeneity in these active glassy systems, and another some simulation results on the soft active glassy systems. So active glasses of self-propelled particles, and there are many biological systems which can be conveniently modeled via this type of system. So for example, proteins, cells, vertically vibrated rods, school of fish, birds, etc. So these systems have the self-propulsion force F0 and the persistence time tau p. And there are many works that has been done in this direction. Several works I have pointed out here by Ludovic Barthier and Kurchan. This is from the group of Chandan and Madan, and this is again by Plenar, Jamel and Barthier. So the main aspect from the perspective of the relaxation dynamics is that both simulation and extended analytical theories have shown that the relaxation dynamics remain qualitatively similar to the equilibrium system at a suitably defined effective temperature. Now, I am going to talk about this analytical direction via mode coupling theory. And this mode coupling theory is one of the theory of glass, and we have extended it for active system. And actually, there are several variants of this active mode coupling theory, and several groups have developed this theory for the active system, and there are some here listed. There are some differences between these different approaches, which shows that the mode coupling approximations are non-trivial for the non-equilibrium active systems. So the approach that we have taken is the following, that we write down the general theory for the non-equilibrium system. So this should even apply for an aging system. It doesn't require any approximation of the equilibrium. And then we take the limit of the infinite time. So then we go to the steady state. and then obtain the non-equilibrium mode coupling theory for the active classes. So the main point that within this derivation is that there is no approximation of the fluctuation dissipation theorem, and therefore the theory should be applicable for the steady state in out of equilibrium. But the cost that we must pay for that is that the theory becomes in terms of both the correlation and the response function. So it becomes much more complicated. And this is the generic form for the schematic version of the theory. So this is the correlation function, this is the integrated response function. So we write in terms of f because of some technical reason for the numerical solution. So here this is the T effective, which is the effective temperature, but this is actually not some parameter that we are defining. We obtain it at each time step via this extended generalized fluctuation dissipation relation. And the characteristic of this theory, for example, we can calculate this T effective from the numerical solution of the theory. T effective becomes equal to the equilibrium temperature when time is very, very small, but then at large time it crosses over to some other value, which is this determined by the activity parameter. Yeah. Yeah, this is the ratio of the APT. No, I mean just generalized form of that, yes. And so we can then write down the scaling argument of the mode coupling theory via using this T effective parameter, and these are the scaling arguments, the lines, and the symbols are the numerical solution of the mode coupling theory. So we can also calculate this long time value. So here you see this long time value of this T effective. So this is determined by the activity. And this we could calculate also within a simplified analytical calculation, where we consider one single active particle trapped in a confined harmonic potential. Using this, we could calculate the analytical forms for the two types of activity, and here the comparison with the numerical solution of the mode coupling theory and this analytical form.
You say you use the correlation function in space and time as essentially parameters of your theory.
Sorry, can we
did I understand correctly? In your mode coupling theory, you said the correlation functions are input.
Correlation functions we are calculating.
And I misunderstood. Can you please go back a slide?
Yeah, so the correlation functions, this is the correlation function, this is the equation of motion for the correlation function. You can calculate it with giving some initial condition like at t equals to 0, it is 1, and then the theory gives you the correlation function.
But here it's coupled.
Yes, so you can solve it there. Right, so you must solve for both C and F at the same time, so it becomes slightly more complicated, but it can be done. Yeah.
Can I actually quickly follow up here? So I know that you're doing it through the mode coupling theory, but the picture of, like plot F versus C, and then you see the slope changing.
Yeah.
It's similar to this from your time vector.
Yes. So this is in some form it looks somewhat like this. So this T effective will change, the slope will be the T effective. Yes. Okay, so then we compared with the simulation results, and here the comparison. So the lines are the scaling relations of coming from the mode coupling theory using this T effective, and the symbols are the simulation data, and they seem to agree quite well with this effective temperature like scenario. However, with the same simulations, there is one particular aspect for the dynamical heterogeneity. So dynamical heterogeneity here means this chi4, the behavior of chi4. One would expect that if the relaxation time is same, then the dynamical heterogeneity length scale or the correlation volume should be similar for those systems. And what for the active system we see is quite different. So we defined some set of parameters in the simulation in such a way that the system will have similar effective temperature, and in that case we expect that the relaxation time will be similar, and this is exactly what we see, that Q of t nearly overlap with each other. From here we can define the relaxation time, and those will be similar. However, for those systems the chi4 t, so this is characterizing the dynamical heterogeneity, they seem to be quite different, and this is what we wanted to understand, what is the reason. And then we write down the, sorry, this is quite messy slide, just wanted to show the structure of the theory. We extended the mode coupling theory for the dynamical heterogeneity of the system, and the calculation is done by my student Soumitra, and then we also compared with the simulation data which is done by Puneet. So we follow the IMCT inhomogeneous mode coupling theory formalism developed by Julio and others. Here is the reference. And so here we apply a small perturbing field and write down the correlation and the response function in the presence of the field. And from there we compute the susceptibilities, and those are the, so those are actually 3-point correlation function, but one can show that they have similar critical properties as the 4-point correlation function. So this, for example, following these two papers, one can show that they have similar critical properties. This is the generic form of the theory for the susceptibilities. Now the important point here is these memory kernel. So these will appear here, for example, here and here. And this last part of this memory kernel is new for the active system. So this is the main point, that if it is not active, then this term will be 0, the second part. And in that case, both the relaxation dynamics and the susceptibilities, they will both be described by this effective temperature scenario. However, since this presence of this term, this actually makes the non-trivial contribution to the system. And this we could also calculate via within the mode coupling theory itself, and this has this particular form that we see. So these are the solution. So the main point is that if this term is very, very small, then still the effective temperature scenario will work for both tau and for both relaxation time as well as the dynamical heterogeneity. But in principle, it can be different. So they have different origin, dynamical heterogeneity and the relaxation time, because of the presence of this non-zero value of this term. And so this is coming from mode coupling theory. So then one can solve the theory again. So the point again that if K1, so this numerical value of this term K1, if we vary, so if K1 is small, 0.6 within this set of parameters that we are using is small, so then the effective temperature scenario still applies, this line, and if we take a larger value, then it basically deviates. So and then we compared with simulation as well, and the similar scenario that when we go to defined value, then in principle, when the relaxation time is being described by the effective temperature scenario, not chi4 peak is not being described in a similar way. So we wanted to understand in a somewhat more detail of what it means and what is the actual origin that is coming from. So we wrote down a model known as the elastoplastic model, and this part of the work is in collaboration with Peter Solich, and Tanmoy, my student, did the simulations. So here this is the elastoplastic model for active glasses, and we followed this recently developed thermal elastoplastic model by Julio and Misaki Ozawa to go to the active system. So here we subdivide the system into different blocks. Each block is associated with a stress sigma I. The main characteristic of the activity is the following, that each of the block, they have the stress, but we associate also a stress rate which is active. So this has this exponential correlation function with a persistence time tau pb, and then there is the yielding via the barrier crossing. So a site relaxes with probability y with this type of scenario. If sigma I is less than sigma c, then it is exponential at a effective temperature T effective, and if it is greater than sigma c, then the probability is 1. Delta EI is given by the distance from this critical point, and if the site yields, then the stress on that site is decreased by this amount, and that stress is redistributed throughout the other sites. And the third element of the activity is that the yielding direction of this of each of the site that has a rotational diffusion with a persistence time tau p psi, and tau p psi has this type of psi has this dynamics with the persistence time tau p psi. So then we can solve it, but the point is that you don't need all the elements to actually reproduce most of the simulation data. Here we have taken a minimal model where we set T effective to the equilibrium temperature T and tau p psi to 0, and that already reproduces most of the known simulation results of the active system. For example, here the persistence as a function of time being plotted, and these are the relaxation time, and the lines are the mode coupling plot with the effective temperature scenario. But the point I wanted to highlight here is the following, the dependence of the dynamical heterogeneity within this model. So within this model, this tau p psi, this rotation persistence time of the rotation of the yielding direction, that basically determines what is the dynamical heterogeneity in the system. So if we increase tau p psi, relaxation time increases a bit, but then it saturates. So it still relaxes with a slightly higher relaxation time. On the other hand, if I take tau p psi to be very large, then the chi4 peak decreases. And in the limit, when I take tau p psi to infinity, then chi4 peak does not increase at all. So they are of course taken some extreme values to illustrate the point, but the main point here is that the direction of the yielding direction basically, or persistence time of the yielding direction determines what is the dynamical heterogeneity in this system. Okay. So that was about the dynamical heterogeneity, and I want to highlight another small story about this on a active soft sphere particle system. How much time I have? Around 10 minutes? Okay, okay, thanks. So this part of the work is done in collaboration with Ludovic, and Puneet did all the simulations. Here we wanted to use a system to interpolate between two types of systems. One is hard sphere system and another this Lennard-Jones type of system. The model is already used in 2009 by Ludovic and Gilles Tarjous in this paper, the detail one can find. So also one can use the active version of this, and this active version also was used in 2017 by Ludovic, Flener and Jamel in the New Journal of Physics paper. And so here we are using the same model as in this paper, active system of WCA particle, WCA potential, Weeks, Chandler, Anderson potential. And another motivation of using this is that in the dense limit of this model, one can go to this, one can approximate the system towards this epithelial system. So that is a long-term goal, but I am not going to talk about that part today. Here activity is included as a Ornstein-Uhlenbeck process. So Ri dot is, so this is the friction coefficient that we set to 1, and this is the sum of the forces. This is the active part of the force, and active forcing basically has this Ornstein-Uhlenbeck process, and this gives a force-force correlation with the exponential correlation with the persistence time being tau p. Now we consider a 3-dimensional binary system with 50-50 particle mixture by number ratio and simulate the athermal limit of the system. So T equals to 0. So the control parameter in our system is F naught, tau p and phi. So the cell propulsion force, persistence time and the packing fraction phi. We first characterize the dynamics via the self-intermediate scattering function Fskt and also the mean square displacement for the entire phase space. So the mean square displacement defined here has this type of form. When we increase tau p for a particular packing fraction and for self propulsion force, increasing tau p basically moves them from left to right. For the Fskt, so this is again defined here, with increasing tau p, so this is the 0 tau p, and then with increasing tau p, initially the Fskt decreases, moves in the left direction, and then beyond a certain point, with increasing tau p, it again moves up. So that from Fskt now I can define a relaxation time, where we have taken the definition tau alpha when Fskt becomes 0.3, and from there I can now plot tau alpha as a function of tau p. So it shows a reentrant or non-monotonic behavior. So first tau alpha decreases with increasing tau p, and then suddenly it starts increasing. So this is a reentrant behavior, and this is not, we are not showing it first time. Several people have already reported this reentrant behavior. For example, Ludovic himself, also in this paper, Flener, Jamel, Barthier, also the group of Janssen and Rajesh, they have also shown this reentrant type of behavior in active system. However, the main mechanism remained unclear. What is the mechanism that leading to the non-monotonic behavior? So we first wanted to understand what is the phase diagram of the system and to understand in which regime we are. So what we do is take a particular value of tau p, and then for a fixed f naught, we increase phi and obtain the relaxation time. So these are with fixed f naught and increasing phi, the relaxation time that we obtain. And from there we fit the VFT form. So this is the VFT form, and then we get this critical point phi c. So this line shows this set of phi c for a particular value of tau p, and then we change tau p and obtain this type of curve f naught square and phi plane. Notice one point that if f naught square is very, very small, then with increasing tau p, this phi c, they go from small to large value. But when f naught is large, then in that case, the phi c goes from large to small value. So they are opposite in the two limits. Now, we wanted to understand one particular point. So what happens when f naught tends to 0? And for that, we fit this particular form. We have some argument, but let me skip that argument in the interest of time. So this particular form we are fitting with this. If you set f naught to 0, then this phi c equals to phi d tau p in that limit. So, we can simply read out what is the value of phi d tau p, and we get the A, phi d and beta as fitting parameter for each of the fit, and the fits are the lines actually, they fit quite well. From there, this particular phi d as a function of tau p, so it saturates at very small value of tau p, saturates to this equilibrium limit, and then it again increases and saturates to the large tau p limit. So, this type of form, and A tau p basically increases with tau p, and beta tau p has slightly non-monotonic behavior, and these are coming from the fit. And where we also give some analytical parallel form just to understand how to write it analytically, and then we can get the 3D phase diagram and we can plot it analytically, we can go any regime, and this is the 3D phase diagram. So, this z axis is log f naught square, this from this side to this side log tau p increases and phi increases from left to right, and this is the phase diagram. So, this particular aspect that at very small f naught square with increasing tau p, phi increases. So, this is the trajectory, and when f naught square is large, then phi decreases. So, a similar phase diagram was also similar to this, was also obtained in that 2017 paper by Ludovic Flener and Zabel via the consideration of the diffusivity of the system. Okay, now what are the consequences of this phase diagram? And the first consequence is a crossover from super-arrhenius to sub-arrhenius behavior. So, if we plot for a particular density, where this phi equals to 0.6 to 5 is small density, in that case the curves fall above this Arrhenius line. So, Arrhenius will be the straight line in this plot, and all the curves with increasing tau p, it falls above this Arrhenius line, and as we increase tau p, it goes from this lower to the upper direction, in that direction. And that feature remains same, but where they fall now changes with increasing phi. So, for example, 0.650, some of them are super-arrhenius, some of them are sub-arrhenius. So, is for this one, and for very large density they remain super-arrhenius, although they change with tau p. So, what is happening that at small phi they all seems to remain sub-arrhenius, at large phi they all seem to remain super-arrhenius, and for intermediate densities there is a crossover from super-arrhenius to sub-arrhenius as we increase tau p for both these densities. And so, a similar behavior was also obtained for the equilibrium system. So, this connects different aspect of different physics. So, in the equilibrium system of soft sphere, this similar behavior was obtained for varying density, but here we are not varying density, for a fixed density we are varying tau p. In that, so this is this paper, but they are written in EPL 2009, also there is a subsequent paper in PRE 2009. So, they showed that a well-defined critical packing fraction phi naught in the limit t tending to 0 that exists and controls this sub to super-arrhenius transition, this crossover. And this particular point phi naught they call the glass point or point G. Now, what is happening in the active system is that this sub to super-arrhenius, this changes given a particular density. As I change tau p, then the behavior of the system changes from sub to super-arrhenius. So, now here we do not have temperature because we are simulating a thermal system. Instead, we have effective temperature. So, we can plot all these data in a plot. So, log of tau as a function of 1 over T effective. And the point that we are trying to understand is, can we obtain a similar data collapse and try to obtain this glass point for the system at hand for the active system. So, this is what we did, and this is how the analysis goes. So, you write down a scaling form and as a function of phi minus phi naught. So, here we are saying that for each tau p, the functional form of this f plus minus, the functional form remains same, but each of these coefficients, this exponent and this phi naught, they now start becoming dependent on tau p. So, assuming that, we could actually collapse all the data in this type of curves, where this branch shows the super-arrhenius behavior and the sub-arrhenius behavior, but for each tau p we get a particular phi naught. So, for the active system there is a glass point for each of tau p, and this leads to a continuum of glass points. So, instead of a particular point, glass point that in the equilibrium system they have shown, we now get a glass point as a function of tau p. So, instead of one point we now get a glass line. And another aspect of or the characteristic or the is that this reentrant glassy dynamics. Reentered glassy dynamics, basically that we showed at the beginning of this section, that the relaxation time first decreases and then starts increasing, and this is also a consequence of this particular dependence of tau p dependence of this phase diagram. So this phase diagram that we obtained earlier is f naught square as function of this, but we can now write down the phase VFT critical point, this phi c, as a function of this phi naught square by a tau p, and this is the exponent that we already obtained, and this phi d tau p. So each of these are already obtained, and then we can now use this VFT form log tau alpha as a function of a plus b by phi c minus phi, and in the phi c we can simply use this expression. So this is the expression that we finally get. And this has two parts which compete is just nearly done. So in this part of the function, so this is like the effective temperature like term. So f naught square by this a tau p, that tau p increases, a or tau p increases as tau p is larger. So this part only increases at larger tau p, but at very small tau p it remains nearly constant. But phi d increases at small tau p, but and then goes to a constant. So what is happening, if we start increasing tau p at small tau p, phi d will increase. So it basically moves the system away from the critical point, and that melts the system, the glassy system. So if I start increasing with tau p, when tau p is small, since phi d is increasing, then it is going away from the glass point, from the VFT point, and then the relaxation time decreases. Eventually this term becomes constant, and this term, this effective temperature like term, that starts decreasing. So this will again increase the relaxation time. So because of this part it first decreases, and then because of this first part it again starts increasing. So these in this plot the lines are the plot of this one. So all of these coefficient a, b, a, beta, phi d, etc., all of them are already determined previously. So these are not simple fit, these are plot of that expression that we already had, and the symbols are the simulation data. Okay, so to conclude, in the first part I talked about the dynamical heterogeneity of the system, and we showed that two distinct mechanisms control the relaxation dynamics and the dynamical heterogeneity in active classes, although the difference can be small. So if the difference of that particular term sigma a that we talked about, if the difference is small, then still the T effective temperature like scenario still applies, and it will be like nearly equilibrium scenario at a suitably defined effective temperature. But in principle they can be different, and we showed also within the elastoplastic model. In the second part we talked about this tau p dependence of the critical line, phi d tau p in principle, in the limit f naught tending to 0 limit. So this leads to several non-trivial active glassy behavior. So this is important to understand how this critical point behaves in the f naught tending to 0 limit, to understand these several aspects. Here we have talked about the two of them, sub to super arrhenius crossover and the reentrant glassy dynamics. Okay, so thanks.